So we've certainly talked in the past about how we can use the derivative, the first derivative, to find local mins and local maxes of functions. And now we're just going to get real into that and make it real sort of rigorous. So just for a visualization, I don't think I need to give you the technical definition for what a local max is. It's a local max if it's bigger than all the other function values around it. It's a local min if it's smaller than any of the other function values around it. We refer to like a global min of a function or an absolute minimum if it is the smallest value of the function period. But we don't really get too into that because different functions are different and you just have to go on a case-by-case basis. Some functions don't have a global min or a global max. If you look at the endpoints of this little function I've drawn for you here, that left endpoint doesn't really look like a traditional like global max, but it would count as one because it's bigger than any other function value, and it does appear to be in the domain of the function. So functions can just cut off, and that still counts as a max or a min. Okay, so we've seen this before. If a function has a local max or a local min at somewhere, and if the derivative exists there, that's kind of the important part, then the derivative must equal 0. So if you look at those 3 points in the middle there, the normal looking ones, we know that the tangent line is horizontal there. That's one of the first things we said about tangent lines. It looks like the function is nice and smooth and the derivative is defined at all 3 of those middle maxes and mins. So that means that the slope of the tangent line is 0, horizontal, and that the derivative should be 0 there. So this is Fermat's theorem. Don't think about this as something you have to memorize. It's just an important one. Fermat was one of Newton's teachers who probably came up with most of the concepts of calculus himself, but never really bothered to write them down, so he doesn't get as much of the credit. But we have to get really into this theorem because it's like what the theorem doesn't say is more important than kind of what it does say. So the converse of if A then B is if B then A. So the converse of this theorem is true sometimes, but it's not always true, which means it's not a theorem. So just because f prime of c equals 0 doesn't mean that's a local max or a min. And just because there is a local max or a min, you could still have it where the derivative doesn't even exist. So you can have a max or a min where the derivative isn't 0, but only in the case where the derivative isn't defined. Okay, and I'm going to show you examples. And also, you can have the derivative being 0 and have it not be a max or a min, right? So we have to be really careful. For example, good old x cubed. Just picture a tangent line to that thing, and then it looks like at the origin the curve flattens out. It doesn't quite flatten out, but it looks like it does. But if you can picture a tangent line moving along that curve right at the origin, it should be perfectly horizontal, which means the derivative, f prime of 0, should be 0. And it is, because the derivative of x cubed is 3x squared. So f prime of 0 is 0. So we do have a horizontal tangent there, but not a max or a min. So that can happen if the function sort of does that thing where it stops and keeps going, like odd-valued polynomials do. You will find that derivative is 0, but you have to just look at it and say, wait a minute, that's not a max or a min. So here's the other case. This is the function cube root of x squared. And if you look at that, it does kind of what the absolute value function did, where it spikes right at the origin. And we know that that means that the derivative isn't defined there, right? We know if there's a kink or a spike like that, then you can't really have a tangent line there. And that bears out when you actually look at the derivative. But that still counts as a local min, right? 0 is in the domain of this function. The cube root of 0 is 0. That's fine. So there absolutely is a local and a global min right at the origin. So this is a case where you can't just find the places where the derivative is 0 and think that you found everything, because here's a place where there is no derivative, but it still totally is a min of the function. So this doesn't always happen at the origin. It can happen anywhere. That's just the simple examples I'm showing you. So if you look at f prime, the cube root x squared is the same as x to the 2/3. So f prime is 2/3 x to the negative 1/3. And now, like in the past, I would have said, okay, just leave it like that. That's fine to leave the derivative like that. But now we want to get a little more into doing stuff with derivatives. That's kind of what this whole section is about, is applications. So if we rewrite that as a radical, that's the same as 2/3 times the cube root of x. Now you can see that at 0, that breaks the rules, right? If x is 0, the cube root of 0 is 0, but now we're dividing by 0. So f prime of 0 does not exist. Okay, so none of that breaks Fermat's theorem. We have a local min of this function, but f prime of 0 doesn't exist. If you go back and look at the wording of Fermat's theorem, it doesn't say that can't happen, right? And, you know, we have, in the case of x cubed, we have a spot where f prime does equal 0, but we don't have a max or a min. So all Fermat's theorem says is, okay, if there's a min and the derivative exists, then the derivative has to be 0. It doesn't say that if the derivative is 0, there has to be a max, right? And it doesn't say that the derivative is defined at every max or min, because here's one where it's not. But that's okay. Don't let this confuse you. We're just basically going to use the graph and then use the calculus to confirm what we can already kind of tell by looking at the graph. Okay, new definition. A critical number of a function f is any number c that is in the domain of f. That could be important. So it has to be in its domain such that either f prime is 0 or f prime doesn't exist. So if f primacy is 0, or if the derivative doesn't exist there, if the function exists but the derivative doesn't, like that last example we saw, that counts as a critical number. And what we do when we look for maxes and mins, we do a couple things. We set the derivative equal to 0. We're still going to do that. And we also look for these critical numbers, which is either that or a place where it doesn't exist, but the function does. It turns out that if a max or a min is to happen at all, it has to happen at a critical number. Okay, so let's get into this. We're going to find all the critical numbers of f of x equals x minus 3 times the cube root of x. So with basically every problem in this entire chapter, in this entire section, the very first thing you're going to do is take the derivative. You're going to need it for something. That's why we spent so much time on these things. So right off the bat, just find f prime. I do want to look at the graph of this thing. You get the intuition that, okay, there's definitely a max at -1, right? There's definitely a min at 1. It looks like it. And there's definitely something happening at the origin. It's not a max or a min, but what it looks like is, it looks like we've seen this before, a vertical tangent, like cube root functions can have. So that's probably a spot. Remember, a vertical line can't have slope. So the derivative might just not exist at the origin, right? But that's not a max or a min. It's just going to be a critical number that we have to look at. And my thing is just to look at the graph, and we're just using the math to confirm what we can kind of see. Okay, so always finding f prime. So the cube root x is x to the 1/3. So that's 1 minus 3 times 1/3 x to the negative 2/3. That simplifies a bit. And again, I want to write this back in radical notation because now I have to do stuff with this derivative. I'm not just doing the derivative and then leaving it because that's the answer. I have to work with it now. So if you look at that, we're going to set it equal to 0 and solve it. In fact, you're almost always going to do that. If we're talking about mins and maxes, you're going to end up doing that no matter what. So get used to doing that. It's algebra. But if you just look at this thing now, it should jump out at you. What number can't we put in for x, right? It's the obvious one. X cannot be 0 because now it's in a denominator. In the original function, x could be 0. F of 0 is just 0 because the cube root of 0 is 0. But we can't divide by the cube root of 0. So that's not really algebra. That's just knowing what to look for. And you know what to look for. Dividing by x. It's the one thing since time immemorial that we're like, well, you can't do that. Okay, so you just have to notice that. Be like, is there any spots where f prime is not defined that the function is? And yeah, 0. So that's a critical number, right? F prime of 0 does not exist, so we found our first critical number. Okay, and now we do algebra. So there's a different ways to solve this equation. Keep it simple. I'm just going to move that rooty looking term to the other side. And then you can think about this next thing as cross multiplying. That denominator times 1 equals 1 times 1. If you just look at that for a second, you have to have that the cube root of x squared equals 1, right? 1 equals 1 over 1. You got to be a little careful here because cubing and square rooting and stuff acts differently. You can go ahead and cube both sides of any equation because cubing is a one-to-one process and you don't have to worry about any kind of plus or minus or extraneous whatever. So you can just get rid of that cube root. The cube root of 1 is 1, and that's the only number that 1 is the cube root of. Okay, so you cube both sides, you have x squared equals 1, and now you do have to worry about when you square root both sides that x is, there's two solutions for that, x is plus or minus 1. Okay, so however you think about that, you should be comfortable doing that kind of algebra. And again, you already saw the graph, so you know what the answer is, right? You know there's a horizontal tangent at -1 and there's a horizontal tangent of 1. So that's why I like to look at the graph first, because then it's hard to really screw it up. It's like you know what you're looking for. I just need to see those steps. You can't just look at the graph. I need to see your algebra. Okay, so that's all three of them. The critical numbers are -1, 0, and 1. In the future, we'll summarize. We'll be like, okay, there's a max at -1, 2. There's essentially a vertical tangent at the origin, and then there's a min at 1, -2. But for right now, all we were asked to do is to find the critical numbers. So we did it. That's all three of them. Okay, so here's the type of problem we're going to be. So this is the type of problem we can do now. And this is the kind of thing that's going to be on the next test. So find all mins and maxes of this function, sine squared of x plus cosine of x. And since this is a periodic function, I'm going to say just find it between 0 and 2 pi. So just the ones you can see in front of you. Right, this thing keeps repeating. So again, you can kind of look at the graph and know at least how many things there should be. You can right away say there's a local min at x equals 0. There's a local max somewhere before pi over 2. There's a local min at x equals pi. It looks like at pi -1. There's a local max again, well, we don't really know. That's why we need calculus somewhere in the middle there. And then there's another local min at 2 pi, which should make sense because it just starts repeating there. So if you just put that, you won't get any points because that's just looking at a graph. Right, now we have the tools to actually figure out exactly where these things are, to essentially prove what we can see with our eyes. Okay, so there's no funny business with undefined stuff here. You know, trig functions don't really have that kind of a problem, and you can see that. There's no vertical tangents or anything, or spikes. So take the derivative. There it is. That should be so easy that you don't even have to think about it at this point. So it's 2 sine x times cosine of x minus sine of x. And then you're solving an equation. So all I'm asking you to do for this first part here is just to solve an equation. Find the derivative, set it equal to 0. Again, you're going to do that over and over again in calculus, so that never goes away. And then just solve this thing. So we need to have our algebra skills on point. So you factor now. Do not divide by sine, because if you divide by something that has a variable in it, you lose solution. So factor out a sine. You get sine of x times 2 cosine of x minus 1 equals 0. I think I can skip a step here. Yeah. So from that, either sine of x equals 0 or 2 cosine of x minus 1 equals 0. I skipped the part where I put the 1 over there and divided by 2. Just convince yourself that 2 cosine of x minus 1 equals 0 is the same thing as saying cosine of x equals 1/2. You've done this kind of thing so many times that at this point it should be pretty quick. Okay, so that's what happens when you factor. You have two possibilities and you have to look at them both. So from the first possibility, sine of x is 0 at any multiple of pi. So 0, pi, 2 pi. And then maybe have a unit circle handy. I don't expect you to memorize all that stuff on there, but cosine of x is 1/2 at pi over 3, and also down in the fourth quadrant at 5 pi over 3. So if you had to do that on a test or something, I would give you a unit circle. Okay, so we're not done, and this is a spot where I'm going to be kind of finicky, and people forget to do this and they lose points. The minimum value of the function is not the x value. So if you look at x equals pi, for example, you can absolutely see that there's a local minimum there, right? But the minimum value is -1. That's the minimum of the function. It's not pi. It occurs when x is pi, but that's not the minimum value. So I kind of insist with all of these that you go back in and just plug. So we got 5 numbers. We got 5 critical numbers for the function. Plug all those back into the original function. That's really just kind of plugging and chugging, but you still have to do it, because not only do I want to see the minimum value, but I want to see the exact value. For example, if you look at, so pi over 3 is that first max you see on the left there, but what is the y value there? It's hard to tell. So now we know that the x value is pi over 3. We did the math. The y value, we still don't know, but I want to know that because that's the actual maximum value of the function. So if you think about optimization in real life, if you found like the sweet spot where your company makes the most profits, you would not only want to know that sweet spot, but you would want to know what that maximum profit is, right? That's the important part. So we want to find both the x value and the y value. Just don't forget that, because it is just plugging stuff in, but don't forget it. So I'm just going to kind of breeze through this. You can use a calculator here. I just be careful with things like pi. So f of 0 is just cosine of 0, which is 1. You can see that from the graph. F of pi over 3, we got to remember some trig stuff here. Sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1/2. Again, just Google unit circle if you don't have one handy. So that turns out to be 3/4 plus 1/2, which is 5/4. So, right, we couldn't exactly tell that by looking on the graph. Now you can kind of cheat and use your calculator, use the max function, which is, I won't tell you how to do, look it up, and it'll tell you that it's 1.25. But if you just put that, I'll know you just used a calculator, so don't do that. All right, f of pi, again, it's not hard math. Cosine of pi is -1, sine of pi is 0. And you could see that from the graph. 5 pi over 3, the math turns out exactly the same as it did with pi over 3, right? And look at the graph, they're even. The same thing happens there. So there's another max there at 5 pi over 4. And then f of 2 pi is the same thing as f of 0. So it's just 1. What I'd really like to see at the end of these is a summary like this. You don't have to use complete sentences or anything, but just look at the graph and say, okay, those over 3s, those were maxes. So the point is the max, right? Pi over 3 comma 5/4 is the local max of the function, and 5 pi over 3 comma 5/4 is the other one. And then we have our mins. We have a local min at 0, 1. A local, actually a global min at pi -1, and then another local min because it repeats again at 2 pi comma 1. So this is really the thing I'm looking for. I want to see the math, and then I want to see you just sum up what you already kind of know based on the graph, but we did the math to get these exact numbers. Okay, same exact type of problem. I want to work with some different types of functions because it's not just about factoring polynomials. You have to remember how to solve equations involving trigonometry and logs and all that good stuff. So here's a graph of the function x squared times the natural log of x. So again, just looking at it, know what you're looking for. There's definitely a min somewhere between 0 and 1, right? And this is a place where your calculator would fail you. You can use your calculator to find what it is as a decimal, but if you just put that, I know that you just use your calculator and you don't get any points. You have to use your calculus to figure out the exact value, exactly where is that local min you see. One kind of weird thing here, and this is that if you look at the origin, it appears to just stop at the origin. It does. But it also looks like, hey, wouldn't that count as a local max though? Because it looks like it maxes out at the origin and then stops. However, think about if the function is even defined at the origin. The natural log of 0 is not defined. Remember why that is. Natural logs only take positive numbers. Any log. Any log, the domain is only positives, not 0, not negatives. So the way we define a local max or a critical number or any of that stuff is it has to be in the domain. So even though the limit of the function as it goes to 0 is 0, if you were to look at a table or whatever, or just punch ln of 0 into your calculator, it's undefined. So that doesn't count, right? So we have to be careful, because even though there looks like there is one there, if it's not in the domain of the function, it doesn't count. So all that is to say, every function is different, and don't just use your eyes, because sometimes they can be deceiving. There's only one extrema of this function, and it's the one between 0 and 1. That spot at the origin doesn't count. Take the derivative. You knew you were going to have to do that. You should have already been doing it. You should have been doing it while I was blabbering on the last slide, right? So f prime is the first time, so product rule, first times the derivative of the second plus the derivative of the first times the second. So x squared times 1 over x plus 2x times natural log of x. Clean that up because we got to do stuff with it now. So the first term just simplifies to just x. And now kind of think about critical points again. Is there anywhere this function isn't defined? Sure. Or this derivative, I mean. Yeah, it's not defined at 0, and it's not defined at any negative number either, because it's a log. But neither is f. F also isn't defined at 0, and it isn't defined at any other negative number. So it's only a critical number if the derivative doesn't exist, but the function does. So really, the derivative and the function share a domain, so you're not going to have any spots like that. Right? Everything else is fine. Any positive number can go in here just fine. So that's our f prime, x plus 2x ln of x. Again, you should have already been doing this. You knew you were going to have to do this. Why'd you wait? Don't wait for me. So factor out an x, right? So just factoring is a big deal in this part. You get x times 1 plus 2 times ln of x equals 0. And here again is just algebra stuff. From this, it would appear that x is a solution to this, x equals 0 is a solution, but it's extraneous, and here's why. Right, you would think, okay, either x equals 0 or 1 plus 2 ln of x equals 0. But x equals 0 doesn't work with the logarithm. If you stick that back into the original equation in the last step there, you get something that's undefined. So that's not even a calculus thing. That's just what we call it in algebra, an extraneous solution. It appears to work for the equation, but it wouldn't even go into the original equation because of that natural log. So you could call it an invalid solution or an extraneous solution, or just, X it out and say, no good, throw it in the trash. It just doesn't work for this equation. Okay, so we're left with the only way for this to be true is if 1 plus 2 ln of x equals 0. And now the word is isolate. If you have an equation involving a natural log, you need to undo that natural log, and hopefully you remember how to do that. But before you do that, you have to get it by itself. And that's a two-step process, but I skipped a step because it's easy. So you subtract the 1, then you divide by 2. So you have natural log of x equals negative 1/2. So again, algebra stuff here. That means that, well, the base of that log to the negative 1/2 equals x. So x equals e. That's the base, right? You don't see it. It's e. X equals e to the negative 1/2. If you're not comfortable with that, then you need to brush up on the laws of exponentials and logarithms. Those two statements I just put up there mean the same exact thing. ln of x equals -1/2 and x equals e to the -1/2 are the same exact statement because of how inverses work. They mean the same thing. Okay, so that's the answer. I think it looks a little nicer to write it 1 over the square root of e. Okay, so that number between 0 and 1 where we said, yeah, min must occur there, it looks like it, that's exactly what it is. Your calculator wouldn't tell you that, right? It would tell you the decimal, 0.6 or whatever that is, but I'm not interested in that. I don't care. I don't want to see rounded. I want to see the exact values because you have to do the math to get the exact values. Okay, so that's it. That's where it happens. And then just don't forget you're not done, right? You have to now plug that back into the original function. Right. The minimum value of the function is whatever f of 1 over square root of e is. So just plug that in. To the original thing, right? Not to the derivative, the original thing. So this is just figuring out what the, f of x is. 1 over square root of e squared times the natural log of 1 over square root of e. Don't leave it like that. You can clean that up. The first term squares to just 1 over e. The second term, well, the natural log of e to the -1/2 is by definition -1/2. So the value of the function there is -1 over 2e. Right? Your calculator could tell you that as a decimal, but it sure wouldn't tell you what exactly that decimal is. That's why I always say exact answers. If you see the word exact in a problem, there's not going to be a decimal. It's going to have an e or a pi or a square root of 3 or something like that. I don't want a decimal. Okay, so finally, like the actual answer to this question is 1 over square root of e, comma, 1 over 2e. The point where that min occurs is the min. That's the answer to the question. And then look at that in the graph. Now, again, you can always use your calculator to check. Find the min with your calculator, write down whatever weird decimals those are, and then type 1 over square root of e into your calculator. It's the same. That's what it is. But that's just a check, right? You got to do the math takes. As you can see, it sometimes takes some doing. If it was just a cubic or something, we've already done that and it's easy. But we're getting into it now, so it's not going to be as easy from here on out. Okay, so that's how you find maxes and mins.